Okay, so today we're going to talk about the conformal mapping. Well, so conformal mapping, so in other words, so this is an angle preserving map. So what is an angle preserving map? So suppose that you have so I have a function between two spaces. And well, then just draw, well, suppose that this function is mapping this point from this domain to this point, in the codomain. And just consider any two curves passing through this point. So as well, the first one is maybe this, and the other one maybe that. Then under this mapping F, then each of these two curves must have their images. So goes like this and goes like that. So well, according to the colors of these two maps, these two curves, say that this guy is mapping to this one, and this guy, the red one, is mapping to that one. And a angle preserving map means, well, you can easily consider an angle that is, well, between these two curves. So, well, I have a tangent line for here and tangent line for this guy. And suppose that this angle is theta. And again, I have two tangent lines, and let us also suppose the angle between these guys, these two vectors is also theta. And well, so this is what I mean by the angle has been preserved. Angle has been preserved under this map F. Well, and if this condition is true for every curve and every point from Z0 and W0, then we say this map is an angle preserving. So what is the most important and famous angle preserving map? So I say that it's a Mercator's projection, or in Korean, Mercator Dopa. So why was it considered so popular? So in like 16th and 17th and 17th century, so yeah, well, the Europeans, they really wanted to travel through the vast oceans, and all they had, so they're the most important tool for navigation. Ocean navigation was the compass. But what is the compass? It only tells us the angle given by from the angle of your face and angle, and the line from the North Pole and South Pole. So that is what you call the bearing. So then then suppose that you want to travel from London to, well, Boston, then how can you find your correct bearing in order to get the right destination? And because the Mercator's map was an angle preserving map, so basically what they did was, so if this is a map given by the Mercator's projection, and this is the London, and this is the Boston, then you basically draw lines through here. And then, so if you draw the line, straight line from this point to that point, this point to that point, then you're gonna get some angle, which can be read from your map. And then what you're gonna do is just follow your angle in your compass. And if your compass is like, if your compass is actually giving you the correct angle, and set your navigation so that your compass is giving you precisely this angle from entire duration you will travel, then eventually you can actually get to your destination. So because of this reason, yeah, we know they already knew that Mercator's map was actually horribly wrong. So if you're getting close to the North and South Pole, right? So because of the distortions, and well, our globe is a circle, which has a non-zero positive ray curvature. So you can never be able to get any map from a surface to a non-zero curvature surface to the zero curvature surface. But in spite of that, so they actually really liked the Mercator's projection because of this reason, because the Mercator's map was an angle preserving map. And today, what we're gonna do is we can actually expect the same phenomenon for the analytic functions. So let us consider this scenario. I have a map. And we say this function is an analytic. At this point. And more importantly, we assume that the derivative at this point is non-zero. Okay. So this is my z plane, and this is the w plane, and my function f is a map from the z to w. So I have a map from here to there, and this is zw, and this point is w0, which is the image of the point f of z. Okay, and let me draw any random curve. Let me draw any random curve, namely C, on Z plane and passing through this point. Now, because since my map is a map, so F is a map from this plane to that plane, so I must be able to expect some image of this guy on W plane, say, well, I don't know, maybe like this. Yeah. So this is f of c. And I want to talk about the angle. So which angle? So I want to talk about, so at this point, well, this is a tangent line at this point, and I want to consider an angle of this vector measured from the positive x-axis, right? Okay. So which will be called the theta 0. Okay. Okay. All right. So in order to do that, first I will need to introduce a parametrization of my curve C. So this is a parametrization of curve C. And for simplicity, I will say U plus I, F is U plus I times V. And so I will also say this is xt, since this is a curve on the complex plane, so, well, there must be two component functions, xt and yt. So this is my parameterization of this curve, this guy. And the image curve, because I have the parameterization of this guy, this parameterization also gives us the parameterization of this image curve. So what is that? So which I will call W of t. So which is nothing but the composition of this parameterization under the map F. Then this is x u of xt and yt plus I times v of xt and yt. Okay. All right. Now what I want to do is I want to consider this tangent vector, which is tangent to this point of this curve, f of c. So in order to find that, then we actually need to take a derivative of this parameterization w of t. So, okay, so and since this guy has two component functions, so therefore I will need to actually take advantage of some knowledge from the multivariable calculus. So this is going to be, well, so I actually got to use some chain law. So ux times dx dt and uy times dy dt. So this is about the derivative of this guy with respect to t. And plus now I just carries over. Now I will need to take a derivative of this one. And this is vx times dx dt plus vy dy and dt. Right? Okay. And well, and since my function was assumed to be analytic at this point, so I can now take advantage of the Cauchy and Riemann condition. And uy was minus vx, right? And vy, this guy was u of x. So this is ux times dx dt minus vx dy dt plus I times vx dx dt plus ux dy and dt. All right. Now I will change this final expression something more familiar. Okay, so maybe, yeah, like this. ux plus I times vx times dx dt plus I times dy dt. Okay, let me compare this guy and this guy. These two expressions, are they the same? Well, this times this and this times that. Okay, so I have the negative sign and this times this, which is this and this times that. Okay. Oh, okay, good. All right. Now, can you recognize each of these vectors? Okay. So this vector is actually nothing but the derivative of your function f, and this is x prime, right? So, sorry, this is z prime. So this is f prime of z. So more precisely, yeah, I should be saying times and z prime of t. Okay, so well, this turns out to be nothing but some very easy chain rule. So this is a chain rule applied to this function. But you know, this chain rule is only happens only true because of the Cauchy Riemann equation. And well, in other words, this is true because my function was assumed to be analytic. Okay. Now what? Now I want to consider the argument of each of these two sides of expressions. So okay, so w prime of t0 is f prime of zt0 and z prime of t0. And so, well, basically this complex number is a multiple of this complex number and that complex number. So if you take an argument of the product of two different complex numbers, then its argument is going to be and the addition of these two arguments. Okay. Well, okay, you know, yeah. Actually, I'm not the precise, well, when I'm mentioning the argument of these two sides, because, you know, the argument is not just a number. Precisely speaking, the argument is just a set of numbers, right? But, well, in this case, just choose any nice, well, just choose any branch you like. then you can get actual number. I mean, so if you pick the one, if you pick at least two of these three lines, then the last one is completely different. So this is, so you know what I mean by this. Okay, so, and this is actually true for all such curves in the z-plane, in curve C in z-plane. So therefore, so what I want to do is, just consider two different curves, the C1 and C2. Yeah. I want this guy to be blue. Then this is FC of 2. So what I want to do is this. Well, I can think of a tangent line here and there. So this guy is tangent to the blue one, and this guy is tangent to the red one. And the same, I can consider the same tangent lines on this space, on the W plane. The first one is this, and the second one is that. Well, so if theta 1 and theta 2 are the argument of the z1 prime t0 and so, well, here, so z1 is a parametrization of this red curve in z-plane, and z2 is a parametrization of this blue curve in this z-plane. And, well, you can consider, well, so let me say the argument of this guy and that guy to be theta 1 and theta 2. And, well, phi 1 and phi 2 are the argument of W1 of T0 and W2 of T0. Then theta 2 minus theta 1 is because of this theta 2 minus phi. And since these two numbers must be the same, so therefore theta 2 minus theta 1. Okay. So in this sense, we say every analytic function. So maybe I really tend to say that every analytic function is an angle preserving. This is actually almost true, not exactly true. So why? Can you see any defect in my argument? Well, this is almost true because, but there is one exception. So what is that? Well, there is actually one number such that there is one complex number whose argument is not well defined. Well, what is that? 0. So you cannot define an argument of the 0 number. So therefore, in order to have an angle preserving map, so you're always free to change your parameterization so that your velocity is non-zero. So you do not need to worry about your velocity equals to 0 because you can always change your parameterization. But however, even if you change your parameterization has non-zero velocity, but in that case, if your derivative at this point equals to 0, then this number is not this number may not be defined. Therefore, in that case, the angle preserving property is destroyed when your derivative equals to 0. So this is a very crucial observation. So this last step, this step is actually true only if the derivative at this point equals to non-zero. Okay, great. So, okay, therefore, so now finally, I can finally say that if your analytic function, which has a non-zero derivative at some certain point, then then some very small neighborhood around the point, then your function actually has a angle preserving property. Okay. Okay, good. Now I am happy. So now I am ready to give you the formal definition of the such an angle preserving property, which is called a conformal map. A map f of z is called a conformal map at a point z0 if f is analytic and f prime of z0 is non-zero. Okay. Okay, great. Okay, before I move on, I'm going to show you a little exercise, little example of this conformal angle preserving properties. Sorry. So let me consider this function, fz equals to z squared. So, this function is conformal everywhere but the origin, right? In terms of an x and y coordinate, so this is x plus I times y squared. So this is x squared minus y squared times I times 2 times xy. So this guy is going to be my u. And this guy is going to be my v. Okay. And for convenience, let me choose my point of z0 equals to 1 plus I. In this case, my function is conformal at this point, right? Okay. Let me just consider two curves. So this is my z-plane. This curve is y plus x, and for simplicity, so assuming that x is positive, non-zero, non-negative, and this guy is another one, which is x equals to 1, and y is positive. And this is my point z0. Okay, and my function is a f of z equals to z squared. So what do you think is the image of these two curves under this analytic map? It's u and v. Okay, this is a very interesting exercise. So let me consider. Maybe I should better change the color of these curves. This is red, and say this is blue one. So okay, first I will try to figure out the image of this guy. y is the same as x. Therefore, well, if you plug in into this, then u coordinate is identically going to be 0, right? But however, well, x equals to y, so therefore, the image of this red line is going to be so x something like this. Okay, well, this is so u equals to 0 and v equals to 2 times x squared, and x is greater than or equal to 0. So therefore, this guy is going to be the image of this one. Okay. What about the second one? So this is x equals to 1 and y is positive. So for the second guy, so u is 1 minus y squared and v is identically 0. So what is this? So this is a okay, so this is nothing but a parabola. No. What? Wait, hold on. Okay, something is not right. Oh, sorry, I messed up. So because y is non-zero. Yeah, x equals to 1. So this is 2 times y, and combining this and getting rid of, so this is u is 1 plus 1 over 4 times v squared. Right. Yeah. Good. Correct. Yeah. Sorry, I messed up. So therefore, this is the right picture. And well, what do you think is the image of this guy under this map? So this is 1 plus I squared. Therefore, if you square this, and this point is going to be 2i. Okay. So this is f of z0. Okay. And well, as you can clearly see from this picture, the angle between these two guys, this is 45 degrees, or pi over 4. And so this is the argument of this guy. Well, the the order of the argument is also unchanged, right? Because if this guy is positive and this guy is also positive. So this guy, well, argument of this guy was assumed to be greater than the argument of this one. So same is true for in this picture on the range of this function. So, and well, at this point, what do you think is the tangent vector? This is 2y and 2, and here y is 1. So this is minus 2 comma 2. This vector is minus 2 comma 2, and this vector is just simply 0 and 4. Yeah, this is 0 and 4. And if you measure the angle between these two, well, this is still 45 degrees. Okay. Okay, good. All right. Okay. All right. So why do you even care about this such a conformal angle preserving properties? So because we actually have, excluding today's lecture, we only have 3 lectures left for this semester. And now this is the right time to actually move on to some more practical applications of a complex analysis. So, well, later on, so we're going to study something called the Dirichlet problems. Or, well, what is the Dirichlet problem? So, well, the Dirichlet problem is about finding the solution of the Laplace equation when the boundary condition is given. And in order to deal with that, then we actually, these are some kind of mathematical machinery in order to prepare for such an applications on partial differential equation. And complex functions, well, complex analytic functions, when you have real part and imaginary part, and both of these two functions, you know, these two dies are always harmonic functions. In other words, well, if you take a Laplacians of real or imaginary part, then you're always going to be equal to, they are always going to be 0, right? And being a harmonic function is, well, okay. So being harmonic real and imaginary part, this property is very useful. So when you're dealing with some so-called Laplacian equations. Okay. All right. Okay. So, but actually, before we move on to some practical application, so just let me allow me to just one more theory. So, which is about the local inverses. So, what is that? So, so there is a theory which was introduced in multivariable calculus, and it says, suppose that you have a function from R2 to R2, from 2 dimension to 2 dimension, and well, what is the derivative? The derivative is going to be nothing but 2 by 2 derivative. So which is sometimes we call it as a matrix derivative. And your matrix derivative is a non-singular at some certain point. In other words, if your matrix derivative has the non-zero Jacobian at some point, then that implies, well, around the point, then your function must allow some sort of local inverse, right? Not full inverse, but local inverse. And you have the local inverse, and on top of that, your local inverse also, well, you can actually expect the derivative of your local inverse. Your local inverse must be also differentiable around the point, and the derivative of your local inverse is actually the inverse matrix of your original matrix derivative. So that is what we call the local inverse theorem. And we can actually expect the same thing for the complex functions. But however, in order to get such a nice property, then first of all, we actually need to assume just one thing. In order to have your complex analytic functions have a local inverse, then your derivative of your complex, your derivative of your analytic function must be non-zero. In other words, in order to have a local inverse of the complex analytic function, then your function must be a conformal function. Okay. Okay. So. Okay. No more talking. And okay, time to write. We have to remember that if I have a function from R2 to R2, and this is the matrix derivative. The matrix derivative at point is, so this is a 2 by 2 matrix, right? This is non-singular. And then we say that F has a local inverse at f of x0, and its derivative is df, the inverse matrix of your matrix D. So this is our theory. Okay. So now moving on to the complex analytic functions, we have this theorem. Suppose I have a complex analytic function. I say this is a conformal function. So in other words, the function is analytic and its derivative at this point is non-zero. Then f has a local inverse. I should better give this guy a name. So I will say G, at f of z0. And its derivative at this point is just reciprocal of the derivative. Okay, good. All right. What is the proof? The proof is easy. Well, suppose that this is my f of z. Well, in coordinate, I say u plus I times v. This is so. In other words, yeah, this is x0 times plus I times y0. So what is the derivative? So derivative is ux plus I times v x0 and y0. Oh, sorry, I forgot to put this subscript x. Okay, so, well, okay, this is a, well, even though this is a function from one-dimensional complex number, set of complex number to one-dimensional complex number, but, well, changing it everything to the real, so, well, real numbers, we can actually consider this function as a map from two-dimensional Euclidean space to the two-dimensional Euclidean space. So therefore, it is very reasonable to assume the Jacobian of my function. So, well, what is a Jacobian? Jacobian, well, is J. This is the determinant of the matrix matrix derivative. So ux and uy and vx and vy. So, and ux vy minus uy vx. Okay, hold on. But we have, since we have the Cauchy-Riemann equations, vy is the same as ux. Therefore, this guy is going to be the ux squared and uy minus uy is the same as plus vx. So this guy is also the vx squared. Oh, hold on. So what is this? This is actually the modulus of this complex number. So in other words, this is the derivative squared. Okay, so, well, if your function is analytic, so this is very good to know. So if your function is analytic, then Jacobian turns out to be nothing but the modulus of your complex derivative. Okay. Well, however, in this case, since we are assuming my function is conformal at this point, in other words, the derivative is never be zero. Therefore, that means Jacobian is always non-zero. And if your Jacobian is non-zero, that means your complex, well, matrix derivative is non-singular. Therefore, in this sense, my function allows a local inverse, right? So since f prime of z 0, not 0, so it has a local inverse. Okay, so, well, now I will need to describe this local inverse. This means, so, well, my original function is a u and v. So therefore, the inverse function must be the x. And this x is depending on u and v. And y is also depending on u and v. On some neighborhood of f of z0, such that this assignment is the local inverse of f. Okay, on top of that, so now I want to consider the derivative of this local inverse. Well, so the local inverse of this matrix derivative of this local inverse should be something like this. But you know what? Because of our theory, which was borrowed from the multivariable calculus, this is just the inverse matrix of this original matrix derivative, right? Now, I believe you all know how to find the inverse matrix of this 2x2 matrix. Well, first you need the 1 over the determinant, but you know, in this case, the determinant is ux squared plus vy squared, vx squared and vy minus uy and vx and ux. So, okay, good. All right. From now on, I'm going to call this guy I'm going to give this guy a name. So from now, I will say DJ. So, okay. So let me compare the component entry by entry. So xu is just 1 over j times vy. And xv is minus 1 over j times uy. And yu is 1 over j times vx. And finally, uy is sorry. I forgot to put this negative sign over here. Right? Yeah, good. Thank you. Okay. And uv is 1 over j times ux. Okay, good. Okay, yeah, sorry. Maybe I'm going to give a name for this local inverse. Okay, please allow me to call this local inverse by function g. So g w, well, here w is u plus iv. This is the uv plus I times yu. Is the local inverse. Okay, now what? So let me compare these 4 numbers. xu is the same as xu. So this guy, so can you recognize that this guy is the same as this one? Because yux is the same as vy, right? Because of Cauchy-Riemann condition. So this guy is the same as this one. And also, I guess you can easily recognize that this guy must be the same as this one because of the Cauchy-Riemann equations for these 2 numbers, right? These 2 functions. So therefore, this function satisfying a Cauchy-Riemann conditions on this neighborhood. Therefore, this function is analytic. G satisfies the Cauchy-Riemann equations and is the G derivative, which is xu plus I times yu, which is 1 over j times vy minus I times vx. Okay, and this is 1 over j times vy is assumed to be is the same as ux because of the Cauchy-Riemann condition, and minus IVX just carries over. What is this? Can I change this guy into something more familiar? Probably. And oh, okay. Now I get it. So okay. Okay, right. So well, if you multiply the complex conjugate of this guy to the top and bottom of this fraction, then you can easily see that this guy must be the same as this one. Okay. And this is 1 over f prime. Okay. So we were able to derive the same, exactly analogous conclusion as we did in the freshman calculus, right? So if a analytic function has a non-zero derivative at the point, then it allows a local inverse, and its derivative, which is g prime, is the same as 1 over f prime. Okay. All right, good. So this is something, well, this is one very nice condition, well, the one very nice properties that we can expect from the conformal mappings. All right, good. And this now we are ready to about, now we are about to discuss the harmonic conjugate. So what is a harmonic conjugate? Well, suppose that you have not a complex function, but you suppose that you have two variable function, two variable real value function. And suppose that your real value function is actually harmonic. Then most natural question arises is that if my function can be considered a real part of some analytic function? Yeah, well, do you remember actually this question was a part of the midterm examination? Well, I'm sorry, actually, it turned out that I gave you the questions, so that which was whose concept is not fully developed. But well, if you remember well, then in one of our midterm exam problem was, so well, first of all, you're supposed to verify that this guy is a harmonic, and also you're supposed to show that this guy can never be able to a real part of any analytic function. If the domain of this guy was the entire complex plane minus the origin, right? Do you remember this? Okay, now we are gonna talk about these issues. Finally, sorry about that. Okay, first, I think, yeah, I hope you remember that if f, so I have a function. Suppose that I have an analytic function is analytic. Then u and v, these guys are some, well, yeah, I should better say R2. Yeah, sorry. Then we all know that these two functions are harmonic functions. So uxx plus uyy0 and vxx plus vyy equals to 0. Okay, so what is the harmonic conjugate? I have two harmonic functions. The harmonic functions. If ux is vy and uy is minus of vx on d, then we say, so this is basically the Cauchy-Riemann condition. Then v is said to be a harmonic conjugate of U. So basically, being harmonic conjugate means if any function is a harmonic conjugate to another, then that means the function must be the imaginary part of its conjugate. Imaginary part of the function. All right. And the most obvious corollary of this definition, which can be derived directly from definition, is if V is a harmonic conjugate of U, on domain D, then what we can expect is U plus I times V is analytic. Okay. So let me try a little bit of exercise of finding the harmonic conjugate. The question is, we are supposed to find the harmonic conjugate of my function was ux, y is 2x minus 2xy. Okay, all right. So, okay, before we even get started, so let me try to verify if this guy is indeed a harmonic or not. So, well, I guess, this is easy. Well, just take the second derivative of x. The first derivative of x is 2 minus 2y, and the second derivative equals to 0. And on the other hand, if you take the derivative of y twice, then 0 and this minus 2x, 0. So therefore, yeah, you can easily say this is harmonic. So, U is clearly harmonic function. Now, in order to find the harmonic conjugate, so this is our first condition that we can rely on. Then if you take a derivative of this guy with respect to x, then this is 2 minus 2y is Vy. And if you take indefinite integral to the both sides of this equation with respect to y, then 2y minus y squared plus, there must be some constant, the integration constant. But since this integration constant may be depending on x, but not depending on y, so this is going to be our best candidate for the harmonic conjugate of U, right? What about the second condition? So, well, in order to be a harmonic conjugate, so minus Vx should be Uy. So that means you change the sign of this guy and take a derivative with respect to x, then minus G prime of x should be Uy. So this is U and Uy is minus 2x. Okay. So this implies Gx is just x squared plus some constant. But this time around, this is truly a constant. So it doesn't depending on x nor depending on y. So my harmonic conjugate is okay, hold on, what is this? So minus y, sorry. I'm confused. X squared minus y squared plus 2 times y plus some constancy. Okay, so, well, I hope you to understand that, well, harmonic conjugate is always determined uniquely up to some constant. Okay, so, okay, Okay, great. So this exercise is done. Okay, but I just want to do just one more thing. Well, if you were able to find the harmonic conjugate of some harmonic functions, then u plus I times of v must be some analytic functions. In our case, ux plus I times vxy is what is this? So 2x minus 2xy plus I times x squared minus y squared plus 2y. Okay, so, well, yeah. For simplicity, I will simply just assume that constant equals to 0. Okay, yeah. Well, as always, if z equals to x plus y, then this is going to be what? Then this is f of z. Then f of z should be v squared times I plus 2 times of z, I guess, right? Aha, so this turns out to be, this is nothing but some just polynomial. Not a big deal. Okay, so the question is, so is every harmonic function has its own harmonic conjugate? The answer is no. Well, sorry, I erased this, but well, you know what I mean. So we already have a very nice example, very nice counterexample. The natural log of x squared plus y squared, even though this guy is harmonic, but this guy doesn't allow. Well, yeah, you know, I have to always specify the domain. So see, even though this guy is harmonic, but it doesn't allow any complex conjugate. Now, can you actually find, so therefore, I really want to find a very nice sufficient condition in being able to have a harmonic conjugate of any harmonic functions. And it turns out this is very closely related to the topology of this domain of this guy. And it goes like this. If a harmonic function, well, I should better say U, is defined on a simply connected domain. Do you remember the meaning of the simply connected domain? Yeah, being simply connected means, well, basically it doesn't have any holes. So, well, in other words, your domain can be continuously shrunk to a single point. If your domain is simply connected, then U has a harmonic conjugate. Oh, hold on. So what did I just say? Yeah, sorry. Yeah, I mean, yeah. Simply connected means that the formal definition of being simply connected is every loop which is contained in this domain can be, if every closed curve in the domain can be continuously shrunk to a single point without any obstruction, then that is the definition of being simply connected. So basically having no holes. Well, and as you can see, this domain is not simply connected, right? Okay. Okay, so what is the proof of this? Well, in order to give you the proof, yeah, I will need to give you a quick reminder of the multivariable, the Green's theorem from the multivariable calculus. So what was the Green's theorem? So we have to remember the Green's theorem. I have this is a simply closed domain R, and this is the boundary curve. And it says the double integral of minus of this and q dx is the same as the line integral of this differential one form, right? So this is the Green's theorem, right? So that means if P partial P partial Y is the same as partial Q and partial X, so under this condition, this integrand goes to 0. Therefore, I want to change this condition a little bit. So, well, suppose that this guy, this region, is contained in some slightly larger simply connected domain D. And suppose that in this domain, suppose that this condition is true for every point in the domain. Then, oh, sorry. Oh, sorry, excuse me. If this condition is true for all domain, every point on the domain, then this integral must be true for all closed curve in D, and this last condition is also equivalent to say that this integral depends only on the endpoint of C. Okay. Well, so this last condition is sometimes we say the path independence. And if this condition is true, then it turned out this last condition actually gives us, this last condition, it actually implies, this vector field P, Q allows its own potential function, right? Then we say the vector field F has a potential F, and this F can be defined by so I will need to explain a little bit on this curve C. This curve is any curve from a fixed point x0 and y0 to xy. And gradient of f, which is fx and y, is p and q. So this is our theory. So this is the one who considered to be one of the most important theory from the line integral, right? Yeah. It was quite a lot. Well, I only just say just a few remarks on this integral. Well, usually you can never be able to define your function like this because, basically a priori, this line integral must be probably depending on the shape of C. Not only the endpoint, but also the shape of C. But since we are assuming that our integral is only dependent on the endpoint, in other words, my integral was a path-independent line integral. Therefore, because of this assumption, so we were actually able to define this function like this. And in this case, well, since in this case, since this guy is a potential function of this vector field, therefore, f of x, fx is p, and fy is q. Okay, good. Now, why is it something to do? Is it anything to do with being harmonic conjugate? Yeah. So let me apply the theory like this. So since u is harmonic, why? Oh, okay. Oh, yeah. So because we were assuming that u is a harmonic function. So since u was a harmonic function, so u x plus u y gonna be 0. So u x is minus u y. So minus u derivative with respect to y is the same as ux derivative of x. Okay, so what is this? Now I want to consider a vector field, which is minus uy, whose x component is minus uy, and whose y component is ux. And this is, well, and this x component taken derivative with respect to y is the same as the y component taken derivative with respect to x. And we know they're the same thing, right? So that means for this vector field, the left-hand side of this double integral should be 0, right? Okay, all right. So, so we can say this is conservative. Well, why is it conservative? Well, the easiest answer is because of this. Well, if this guy equals to 0, if this condition is satisfied, then this is conservative. But in the deep inside, we know that this is conservative because this domain is always assumed to be simply connected. Because, in other words, we are pretty sure, 100% sure that this region R does not contain any hole inside, right? Because of this reason, now we know that this guy is conservative. Okay, so being from here to there, so we are actually taking advantage of the domain is simply connected. Okay, so this is simply connected. Then, since this guy is conservative, then this vector field is conservative. Now I want to find its potential function. So minus uy dx plus ux dy. Well, let me say this C is any curve from some fixed point in the domain D to point xy. And I'm going to name this guy to be Vx, y. Well, I must have such a nice function. This is the potential function of f. And since this guy is potential function, therefore, this potential taken derivative with respect to x must be the same as the y component, so x component of this vector field, so which is uy, and the v potential function taken derivative with respect to y must be the same as the y component of this vector field, so which is ux. Okay, now I want you to take a look at these last equations. Well, because of this reason, well, this is exactly the Cauchy-Riemann condition. Therefore, this potential function turns out to be the harmonic conjugate of our function here. All right, great. So, well, so this is another very interesting example of, well, solution of some differential equation depends on the topology of the domain. So what is it? Well, actually, so I want to emphasize this. So being able to find a harmonic conjugate of some harmonic function is actually nothing but just solving some differential equations, satisfying these relations, right? And the solution of this differential equation was strongly dependent on the topology of the domain. This kind of phenomenon happens a lot. Well, especially in differential topology. Okay, okay, but no more rambling. Right. Is so V is the harmonic conjugate. Okay. Okay. Yeah. Well, I don't think this is a good idea to introduce a new topic because I have only 4 minutes left. Sorry about this. Yeah. So please allow me to end a little bit earlier than usual, and I will see you next time. Okay. Thank you.